In problem 2.18, for a particle in a one-dimensional box of length L, we could have put the coordinate origin at the center of the box. Okay, so in the derivation that's done in chapter 2, the particle in a box had origin on the left end of the box, and the right end of the box has L, so that the length of the box is of length L, right? And everything outside the box has a potential infinite. Now, what this question says that is, we could have actually put the origin at the center of the box. So in the first case, the center of the box is at L by 2. Now, this question says the origin can be at the center of the box, which means the box can go from negative L by 2 to L by 2 with a length L, and the center of the box is at origin. So we can have a particle in a box like this as well. Now we need to find the wave functions and energy levels for this choice of origin. So if the box started at negative L over 2 and ended at L over 2, what would be the energies and the wave functions for this kind of a particle in a box? So even before I do the derivation for the wave functions and energies, I think one thing that can be made very clear is that it doesn't really matter where the limits or where the ends of the box or the center of the box is or are. As long as the box is of length L, the wave function and the energy levels are going to remain the same. So by changing the ends of the box, we're not really changing its length. All we're doing is we're just changing the limits of integration and the points at which the boundary conditions are being applied. So that should not really change the very idea of a particle in a one-dimensional box of length L. So that's not going to change any of the wave functions or energy levels. The forms would look slightly different, but they will essentially give you the same wave functions and energy levels. So having clarified this, let me actually draw the particle in a one-dimensional box the right way for this, for clarity, and we can get started with deriving. So this is the center of the box. This is negative L over 2, x is equal to 0, and this is L over 2. The box is of length L. Now the potential is infinite on either side of the box, it's outside the box. The potential is 0 inside the box. Now, the time-independent Schrodinger equation would be this. Now I can write this as I'm just moving things around. So we have something like this. I'm just bringing the energy on this side and I'm moving the derivative term to the other side. And I just I basically brought some terms together. Now, let's call this region 1. Let this be region 2, and let this be region 3. So in regions 1 and 3, right, the wave function let me actually call the wave function here to be psi 1, psi 2, and psi 3, just like the derivation in the book. Okay. Now, if in regions 1 and 3, V is equal to infinite, right? There's infinite potential. That is going to give me h bar squared over 2m times del square, d squared psi over dx squared to be this. Now, this term, it doesn't matter how much you subtract from infinity, it's still going to remain infinite, right? So it's a huge value right there. So I am gonna just write this as infinity, okay? Now that would imply that psi of x would be 1 over infinity times some value. Now this would be 0, right? So that 0 multiplied by anything else is 0, so that gives us the wave function in region 1 is 0, the wave function in region 3 is 0, and these are both the regions outside the box where the potential is infinite. There you're not going to see your wave function. So we're clear on this part, right? Now we need to derive the wave function for region 2. So in region 2, we're going to have the same equation. However, the potential is equal to 0 right now. This entire term is going to be 0. So we will end up with h bar squared over 2m d squared psi over dx squared plus e psi of x to be equal to 0. Now this is of the form of the it's of the form it's a second order differential equation, so it would maybe we can just get rid of this constant here by dividing everything with this. That will give us d squared psi over dx squared plus 2m over h bar squared times e times psi of x is equal to 0. Now this is of the form you can also write it as plus b times some first derivative of y, but because we don't have a first derivative of psi here, b will be zeros, so I just wrote it in this form. And we know that a solution, in this case, c is equal to 2me over h bar square, and y is actually this psi. So the solution for this is going to be of the form e to the power sx, right? And that would give us the auxiliary equation square root of -1 is going to be I root c plus or minus. Right, so if we were to plug in the value of c, we would get so this would be the solution. This would be the value of s. So there are two possible solutions, one positive, like one positive and one negative. So when you have two solutions, the general solution for the differential equation is going to be a constant times the first solution plus another constant times the second solution. So now that we have this we can write, let's say if we have e to the power I theta, this can be written as and e to the power negative I theta can be written as this, right? So we have something similar to e to the power I theta and e to the power negative I theta. So we can actually write x to be C1 times cos of root 2 and e, so h bar, plus C1i sine of root 2 and e, so h bar. There's no root for x. So all I'm doing here is simply writing the exponent part in terms of cosine and sine. Now I can club the cosine parts together, right? And if I did that, I would have something like C1 plus C2 times cosine. And similarly, I can combine the sine part so that I have okay, so I made a mistake here. This will be negative C1 minus C2 because you have an e to the power negative I something. So I can call C1 plus C2 to be a constant A. And I can also call C1 minus C2 to be another constant B. And this will be the form of the wave function, right? However, we don't know what the values of A and B are. So this is the part where we apply the boundary conditions, right? So we know that if we come back here and look at the figure, we know that at negative L over 2 and at L over 2, the wave function has to be 0 because outside the box it's 0 and we want the wave function to be continuous. We don't want to see any crazy jumps in the wave function. So we can assume that I'm going to replace y with psi because it's actually psi. This is psi of 2, psi 2 because it's the wave function inside the box. So psi 2 at x equals negative L by 2 is going to be the same as psi 1 at negative L over 2, which is 0. And psi 2 at x equals L over 2 is going to be the same as psi 3 at x equals L over 2, which is 0. Now let's plug in the values here and see what happens. So 0 would be when x equals negative L over 2, it's going to be a cos. Cos of negative theta is just cos theta. So when you plug in x to be negative L over 2, you'll still have just like cos. So the negative is still going to be cos positive value, cos of the positive values. I'm just not going to write that negative there. And sine of negative theta is actually negative sine theta. So when we have x equals negative L over 2, let's say sine of some thing times negative L over 2, is going to be negative sine of L over 2, something like this. So I'm going to bring the negative sign outside, and this would be this. Now, similarly, this will give me now if I, let me actually call this equation 1 and call this equation 2. Now, if I were to add equations 1 and 2, that would give me 0 to be equal to 2 times a this, because these two terms get canceled, the sign terms get canceled. Now, if I were to divide this whole equation by 2, then yeah, simply do that. Now, another thing I can do would be to subtract the equations, right? That will be the cos terms get subtracted, and I will have negative 2bi sine of root 2ne L over 2h bar. Now, if I divide the whole thing by negative 2i, I can just remove that from here. That's what this equation will be, right? So from these two equations, from this equation, either a is 0 or the cos term is 0. From this equation, either b is 0 or the sine term is 0, right? So if we have a equals 0 from this, and if we have b equals 0 from the second equation, that would imply that the wave function in region 2 is always 0, right? If the wave function has two constants multiplying two terms, and if both the constants are 0, the wave function is always 0. But we know that this is not possible, right? Because the particle must be somewhere inside the box. It cannot, the particle, the wave function cannot be 0 for all the values of x inside the box. For some value of x inside the box, at least for some values, it has to be a finite value. The wave function should exist. Otherwise, we are telling that the particle is nowhere in the box. It's nowhere to be found in the box. But that is not true. You know, the particle is in the box. So this is not a possible option at all, right? Now, similarly, if we chose the cos term to be 0 and the sine term to be 0 in both the cases. Here we are telling that if we chose these two conditions, then that would imply that cos theta is equal to 0, which is equal to sine theta. That's what this would imply, right? The conditions for cos theta to be equal to 0 would imply that theta is some form of, like, let's say theta is m pi over 2, where m is an odd number, right? So theta can be pi over 2, 3 pi over 2, 5 pi over 2, and so on. Now sine theta equals 0. would imply that theta is some form of n pi, where n can be anything, 0, 1, 2, so on. Or theta is going to be 0, pi, 2 pi, 3 pi, 4 pi, and so on. And we know that none of these values can ever be equal to any of the values of theta in these two cases, right? The conditions on theta are so widely different for both sine and cos theta. They're mutually exclusive, right? So for no value of theta, we can have both sine and cos theta to be equal to 0 in this case. So we cannot choose this condition as well because it does not work. That's just not how it works. So the only two possibilities for picking the conditions would be either A equals 0 and the sine term is 0, or B equals 0 and the cos term is 0. So these are the two possible scenarios that can happen. So now if A is equal to 0, right? Let's call these 3 and 4, cases 3 and 4. Now let's study case 3. A is equal to 0 would imply that the wave function is going to be, if A is 0, it's just going to be B times I times sine of x, right? So it's just going to be B times I times this. And we also know that sine root 2m e times L over 2h bar is equal to 0. And that would imply root 2m e times L over 2h bar is equal to n pi, where n 0, 1, 2, 3, and so on. Now that would give us the energy to be n pi times 2h bar over L. So 2me. Yeah, so under root 2me is going to be this. Now, if I were to square both the sides, I will have something like this, right? Now, I can call it n pi to h over 2 pi. H bar is nothing but h over 2 pi, right? Now I can cancel out 2 pi and 2 pi. So this will just be nh over L whole squared. That implies the energy itself is going to be n squared h squared over L squared times 2m. I guess this is a little bit confusing here because of the n, which, okay, that's pretty bad. So I'm just gonna call this, instead of n pi, I'm just gonna call it b pi, okay, and where b can be in these things. So I'm gonna make this correction everywhere. So this would be b squared. Now this is very similar to the energy levels we have for a particle in a box, which are n squared, h squared over 8 and L squared. So we can multiply and divide this equation by 4, right? That will give us now I can write these two as now B cannot be equal to 0 because that would imply the energy is 0, which would imply the wave function is 0 for all values of x inside the box, right? So the wave function is here, right? So this is the wave function. Now, if energy is 0, if B is 0, the energy is going to be 0 and sine of 0 is 0. So irrespective of where you are inside the box, the energy is just going to be 0 for all the values of x inside the box. So this would be the solution. Now, if we were to consider case 4, in case 4, B is equal to 0 and the cost term is equal to 0, right? So B is equal to 0 would give me this wave function. However, we also know that the cost term is 0. That would imply right? So it has to be a multiple of pi over 2, and it has to be an odd multiple of pi over 2. So it's going to be something like this. Now that would mean now if I were to square this whole thing, and this is very similar to the energy of a particle in a box, right? Um, so this would be the energy, and I'm sorry, in the previous case, I did not write the explicit form of the wave function. So now that we know the value of E, the wave function, I'm just going to write the wave function here. The wave function is going to be B times I times sine of root 2me. So root 2me can actually be written as B pi so from this part, I can write root 2me to be equal to B pi over B pi 2h bar over L under root. Okay, I'm actually sorry, there won't be an under root. Sorry. This would just be B pi times 2h bar over L. Now that would be 2 pi B over L times h bar is h over 2 pi. Or actually, I don't think I have to expand that because I can just cancel out the h bar here and here. So that would give me 2 pi B over L times x. So this would be the wave function in this case. And in this case, the wave function would be a times cos root 2 me x over h bar, which would be a times cos. We know root 2me is now I can write h bar to be h over 2 pi, so I can cancel out h, the 2, and the 2. Okay, and this would give me a cos 2n plus 1 times pi x over L. So this would be the wave function. Now the wave function for a particle in a box that is derived in the text was very similar to this, where you have a constant times n pi x over L, right? So in this case, our n derived in the book is actually the equivalent of 2n plus 1 that we have here. So we still have some term times n pi x over L, or in this case, we have b times I times, which b times I can be some constant times sine of 2b is actually the n given in the text is the equivalent of 2b, right, that we have here. So this is still something like b times I times sine of 2b times pi x over L. So our wave function is very similar to what was derived in the book. Now, if we notice that in this part of the equation, 2n plus 1 takes the values of 1, 3, 5, 7, 9, 11, and so on. It takes the values of odd integers, right? Depending on then n equals 0, 1, 2, 3, so on. You can have 2n plus 1 to be 1, 3, 5, 7, and so on. Now, in this case, 2b can take values of 2, 4, 6, 8, 10, 12, and so on. It takes the values of even numbers, right? Because b cannot be 0, then the wave function would be 0. This 2b is only going to take even values, and 2n plus 1 here is going to take odd values. And lastly, these wave functions can be normalized to find out the values of a and b, so that can be done. And we can also take a look at this by plotting them, so we can try plotting them, and they're going to look very similar to the wave functions you have for the particle in a box derivation given in the textbook, where the center of the box is at L by 2. In this case, we have the center of the box to be located at the origin. So we can use the appropriate wave function to describe the even states and the odd states. And if you were to plot them, you'll actually see that they're exactly the same. They're very similar to what you get when you plot the wave functions given in the textbook. Now let's try normalizing these functions. This is what the normalization means, right? So I can combine b times I to be another constant, maybe call it b1, right? And then I can do this. So this would give me this is a normalization condition, right? Now I'm going to focus here on evaluating this integral. So cos 2 theta is 1 minus 2 sine squared theta. So 2 sine squared theta is going to be 1 minus cos 2 theta. So the integral itself can be written as negative infinity to infinity. I'm going to divide this by 2 and multiply this by 2. That shouldn't change anything. So integral of 2 sine squared theta is going to be this. That will be integral negative infinity to infinity dx minus cos 2 theta dx. Now, we know that the integration limits in this case are not strictly from negative infinity to infinity. That's because the box goes from negative L by 2 to L over 2, right? So these limits need to be changed. So I'm going to set the right limits, negative L over 2 to L over 2, this, right? And the theta in this case is 2b pi x over L. So d theta is going to be 2b pi over L times dx. Now, integral dx is just going to be x. I'm going to apply the limits. And I am actually gonna change this a little bit. So it's going to be cos 2 theta times dx is L over 2b pi times d theta. I'm just doing the change of variables. That'll give me L over 2. What's this? Integral of cos okay, the derivative of sine theta is cos theta. So the integral of cos theta is going to be sine theta, right? The integral of cos 2 theta is going to be sine 2 theta divided by 2. So this is going to be now I'm going to write that out explicitly. So this will be L over 2 plus L over 2, which is L. 2 times so this 2 theta here is actually going to be 4b pi x over L. Sine of negative theta is negative sine theta. Now I can cancel out. Now here b is an integer. So 2b times pi is going to be an integer multiple of pi. right? So sine of an integer multiple of pi is always going to be 0. So this entire term is going to be 0. So this will just be equal to L, right? So we started, the value of the integral is L, right? Now that would imply b1 squared over 2 times L is equal to 1, or b1 squared is equal to 2 over L. b1 is equal to 2 over L, the power half. Right? So this is the normalization constant we have when we choose the origin to be at the left end of the box. And we have the same normalization constant when we choose it, when we choose the origin to be at the center of the box as well. Now, you can repeat the same exercise with the other side too, where you have a times cos of something. You can integrate that. Do this and you can find out what A is. So it should be very similar, and this is how we normalize. I just wanted to show one case and you can try the other and you'll find that the wave functions are very similar.